Welcome to the second video on the extension of E2 integration. Here we go. So in this video, we'd like to come back to our example motivating why we want to introduce this space H2 log, which was to integrate for general continuous functions, G or F, Brownian motion, applied to a Brownian motion, T, T. Right? This was our motivating extension, and this is in general, this is here, F is a continuous function. This is not in H2, but what we will see now, or have seen already, is this here is in H2 log. And what I want to show you now is that, well, as we expected, or as we constructed the integral, this integral here is defined as limit of left point Riemann sums, or can be approximated by left point Riemann sums. And of course, then you could make it to the definition, but okay, we defined it differently. Anyway, so let's come to the last theorem here in this section, which is Theorem 3.2.2 about the Riemann sum approximation of the E2 integral. Riemann approximation. Okay. So let's assume F is continuous. Let's write it out. So the function from R to R is a continuous function. And well, we pick a refining sequence of partitions. So this is Tn is defined to be the Ti is just, okay, we divide the interval 0 to t in equidistant with the equidistant points. So this I runs from 0 to n. And then, as we hope for the left point Riemann sum, so if I sum all the increments multiplied with the function f evaluated at the point bti, multiplied with the increment of Brownian motion. Okay. So this is what we understand as Riemann sums, because if you replace the Brownian motion by, for example, just time, so then here would just then ti minus ti minus 1. So this time integral, this would be the classical Riemann integral, but now we integrate with respect to the Brownian motion. So we have here the increment of the Brownian motion. This goes, if n goes to infinity, exactly to our E2 integral. And this conversion holds in probability. Okay, so this is what we are going to show in this video. All right, so let's do this. And the proof is, I mean, it's so short, but it's also not hard because, I mean, we just need to reduce everything to what we have learned in the past videos. So first step is, and I think this is what you expect, because I mean, we did it like several times already. The first step is always to introduce a smart localization so that everything is bounded or integral in the right sense. So first step is we localize everything. So what does this mean here? So here we want to localize the Brownian motion. So we do take a natural number n we set, well, stopping time is the first time to t such that the Brownian motion hits the barrier M, right? So we want to restrict the Brownian motion to the area minus M to M. And to make it a finite stopping time, let's restrict it to minimum to t. Okay, what do we have here then? Well, tau m are stopping times, or is, I mean, here, okay, look at 1. This is the stopping time, right? Because Brownian motion is a continuous process, and this is the hitting time of a closed set. And well, if you look at the sequence, this is a localizing sequence for PM, right? Because I mean, this is what we have seen before, because the Brownian motion is continuous. E is continuous. Okay, we have seen this argument before. In particular, this means, as we have also said in a remark already after our motivating example, this means that F applied to the Brownian motion is in the space H2 log. Right, so this means in particular, well, this here is well defined. Okay, and now I want to introduce a second localization, which is, okay, if we have introduced the stopping time tau m, well, we only need to look at the function f on an interval minus m to m. So for every m, there exists a continuous function fm with compact support. Right, so you can say it takes values in some interval, which finite boundaries. And this is more important, is if I restrict fm to the interval minus m to m, it's identical to the function f on this interval. So what we do is here we localize the function f. And this is fine because, I mean, we only consider the Brownian motion in this interval minus m to m, because after, I mean, we stop at the moment this is not true anymore. Okay, so what do we see here? Fb is equal to f m applied to b on the interval. So on the event that tau m is equal to t. And furthermore, this is why we did this second localization here, is that now, if I apply this compactly supported function to Brownian motion, this is in H2. Okay, that's great. So we reduced basically the proof we wanted to show you. So this, to prove the theory, we wanted to have reduced it now from the class H2 log to the class H2. And now we want to go over to simple functions. So the class of H2 0. This is the second step. So we let us fix in them. In be fixed. So then we can set, we want to introduce simple functions which approximate this function fm applied to the Brownian motion. So this is our phi n. which is defined as the sum from I1 to n of Fm applied to the Brownian motion at the grid points. And then, okay, indicator function of I minus Ti. Yes. And well, we know that this function is in H to 0 for all n. For n in n. Because these are simple step function. I mean, these terms here are adapted, so this works. And what we want to show now is that these phi n converge to Fm applied to the Brownian motion in H2. Okay, so that's the task for the second step. So let's do so. Okay, so let's look at the H2 norm, which is just the expected value of the integral from 0 to t of Fn, psi n minus Fn applied to the Brownian motion square. So this is just the H2 norm. Now I want to estimate this H2 norm to show you if, well, n goes to infinity, this goes to 0. Okay. Let's first plug in the definition of phi n, and then we pull out the sums. So, okay, if we have here a sums from 1 to n of the expected value, now I integrate only from ti minus 1 to ti of m, right? This is m applied to the Brownian motion at ti minus 1 minus fm applied to the Brownian motion at time s squared. So this is definition of phi n. Cool. And now we need to estimate this a bit. So let me, okay, how can we estimate this term here? Let's forget the square for a moment. Okay, this is nothing else than the supremum. I mean, it can be estimated from above, but the supremum over all r in this interval ti minus 1 to ti, and then the difference of tn and tmr. Right? So what we do is we estimate this integrand with its supremum over the intervals ti minus 1 to ti, because then we don't need to, can get rid of the integral. And let's do this. So what do we get? Okay, we have here the intervals here have the length t divided by n, right? This is the length of the interval. Then I have my sum from 1 to n of the expected value of the supremum over all r in ti minus 1 to ti of this difference here. So I just take the blue line and put it here. And I forgot a square. Here we go. Okay. Okay. And now we f is uniformly continuous. Yeah. So let me introduce set the modulo of continuity. Right, so let me introduce f depending on h, which is just a supremum over the difference of fm applied to point x minus fm applied to point y in absolute values for all x, y, and r, which have a distance of x at most h. And the point is, well, if since f is uniformly continuous, because it's a continuous function on a compact set, we know that this modulus of continuity here goes to 0 is h goes to 0. 0. All right. So let's apply this. Right. So what we keep estimating from here to here. So we have Tn t divided by n, the sum from I to n of the expected value of the modulus of continuity of R E of the Brownian motion time, well, let's say R minus T square. Oh, square. Cool. And now we use dominated convergence. At first, okay, 2 steps. So first we estimate now each summand by the maximum of all summands. That's fine. So we lose an n when the summand, so we get here the modulus of continuity of supremum over all and all these time intervals, and then the supremum over all r in ti minus 1 ti of the difference, and then this all square. And now we use dominated convergence, which tells us, okay, if we send h to the n to infinity, which means this h here goes to 0, this goes to 0 by dominated conversion. Right? Because we localized the function f, so fm is bounded, so we can use dominated conversion theory. Okay. Plus, okay. Plus continuity b is continuous. Cool. So we know that our simple functions phi n go in h2 to the function fm applied to the Brownian motion. So what do we know from this? Well, we know in particular that the Riemann sums here of fm applied to Brownian motion at ti multiplied with the increment of the Brownian motion goes to the integral of from 0 to t of fm applied to the Brownian motion integrated with respect to the Brownian motion in L2. Right? This is Ito's isometry. So as n goes to infinity. Right? This is by Ito's isometry, or basically the definition of the integral. Okay, so now we need to get rid of these localizations again. So of the localization of m. And this is the third step. And this is why we lose I mean, here we have the strong L2 conversion, and now we only claimed in the theorem that we have the conversion probability, and this is where we lose it, because reduce. I mean, getting rid of this localization in M will cost us this strong L2 conversions and lead us to the weaker conversion probability. So what do we want to show? I mean, we want to take for all epsilon goes bigger than 0. And we want to introduce the set an epsilon, which is given by difference of this approximation +1 -1 minus the integral of f applied to the Brownian motion bigger than epsilon. So we want to show that this event of an epsilon goes to 0 as n goes to infinity. Right. This is the definition of conversion probability, saying, okay, for every epsilon, this event has a probability of 0. Okay. And now we know on the set that Fm at tau n, so our localization is equal to capital T. We know we have that the integral from the Brownian motion, f integrating the Brownian, f applied to the Brownian motion, integrated with respect to the Brownian motion, is equal to the integral with Fm applied to the Brownian motion. Yeah. This is by our theorem. This is theorem, the last one we proved in the last video, which is the persistency of identity. All right, so we can move stopping times from the inside of the integral to the outside of the integral, and this is exactly what happens here. Well, this is good. So, and what do we have? So if we want to estimate the probability of an epsilon, well, we can estimate, this is the same as the probability of an epsilon intersected with the stopping time being less than t, and the set an epsilon intersected with the complement of this event, so that tau m is equal to t. No? And now we can estimate this from above by, okay, let's make this set a bit bigger so that tau m is less than t. And the set, which I mean, just here we're not getting rid of anything. This is, okay. The good news is this goes to 0 if we send m to infinity, and this goes to 0 if we send n to infinity. This is step 1, and this is step 2. We can combine this to show that if n goes to infinity, this all goes to 0, which completes our proof. So we have shown now that the Riemann sum approximation of continuous function applied to the Brownian motion converges in probability to the E2 integral. All right. I hope you enjoyed the video.